audio in the audio realm consistently rate his transformers really high. Now, this is not a commercial for his transformers, which is good for me because I probably can't afford one. But you may want one after you hear the talk, and I'll let him introduce it. So, David, go ahead.
Okay, we're good, I guess. I will be talking about the an alternative to using the output transformer for tube audio amplifiers. Now, this is not a talk about hybrid amplifiers where which mixes a tube portion with a solid state portion. So that's not what this is about. There's plenty of semiconductors in my amplifiers, but none are used for analog amplification, at least not for the audio signal. Some are used for auto bias and other functions, but not for the audio signal. So I guess we ought to start with the first slide or the next slide. Okay, audio amplifier dilemma. Tubes like high voltage, low current, but speakers like high current and low voltage. Can they talk to each other? Next. So this is a kind of a broad outline of my talk. I'm going to spend a fair amount of time the output transformer, why use one, and then I'm going to talk about the output transformerless amplifier, and then finally the last section is going to be on the ZOTL. The ZOTL is zero hysteresis output transformerless. That's what the letters stand for. And it was coined by a fellow named Harvey Rosenberg, who's no longer with us. And he was he licensed the design of an OTL from Julius Futterman. He started at New York Audio Labs and made amplifiers for a period of time until that went belly up. But he was a great promoter of this, you know, what I was doing. So anyway, let's move on to the next slide. So the part about the output transformer, why use one? Power transfer efficiency. I'm going to give an example of tube current to speaker current and impedance conversion. Now this gets pretty technical in places, so you know, bear with me. Size matters, single-ended versus push-pull, simplified parasitics model of output transformer, frequency response, and special configuration of the ultralinear. Okay, next. Okay, this gets kind of technical, but really you need that to understand it. Let's consider a common output tube, 6V6, which I'm sure a lot of you know if you deal with antique radios. Typical operating current, 40 milliamps, you know, 300 volts maybe. We wish to drive an 8-ohm speaker with this tube. If we connect the tube directly to the speaker, we can ideally have a peak signal current in the voice coil of plus or minus 40 milliamps or 0.04 amps. The power delivered to the speaker can follow either one of these equations, where I squared is current squared times the resistance, which is the resistance of the speaker. Alternatively, power can be the voltage squared over the resistance of the speaker. For this case, the limiting term is current, so the first equation applies. Thus, the peak power delivered to the 8-ohm speaker is 0.012 watts if you use that first equation, where the current squared is the square of 0.04 amps. The RMS value is 0.006 watts, and because RMS is twice the peak, or half the peak rather. Meanwhile, the plate loss in a typical 6V6 operating at 300 volts is the voltage current product, or 12 watts. The efficiency is 0.006 divided by 12 or 0.05%. Next slide. But if I use an output transformer, I can balance those two equations and optimize things to take advantage of the high voltage. The transformer has a property of reflected impedance. So the turns ratio can be selected to make the power term equal for the above two equations. If we assume a peak voltage of plus and minus 300 volts is available on the primary of the transformer, and the plate resistance of the 6V6 is 0, a turns ratio of 30, actually it turns out to be 30.6, would transfer the most power. Of course, you can't have a fractional turn in the transformer. The impedance ratio, which goes as the square of the turns ratio, is 900. The tube sees a speaker load of 7,200 ohms. The peak power is now 12 watts or 6 watts RMS output. In reality, the tube plate impedance is not 0, and the full 300 volt swing is not possible. So perhaps only a third of this power might end up at the speaker. But at 2 watts, the efficiency is 16% with an improvement factor of a whopping 320 by using that transformer. Now, yeah, go ahead to the next slide. Now, instead of a turns ratio 30 in the transformer, you can put 30 tubes and get your current, but probably not terribly cost effective, even though it could be very high quality sound. Next. Small audio output transformer, small sound. Big, heavy, expensive audio output transformer, big sound. Next. Now, I'm going to describe some of the parasitics and push-pull versus single-ended. Push-pull requires 2 tubes and 2 inputs, 1 inverted in phase. Single-ended, just 1 input. The bandwidth of the output transformer is limited at high frequencies by leakage inductance and parasitic capacitances, or both. And yes, both. Low frequencies limited by the magnetizing current, and saturation, or both. And yes, and both. Push-pull can deliver much more power per tube than single-ended. Reason is you can turn the tube on harder than you can really turn it off. I mean, so that's where you can get more power out of the push-pull circuit, is because you're turning one tube on hard, the other tube is kind of drifting off, but it's much more forceful to turn one of those tubes on at higher current than turning the other tube off. So that's why you can get the more power. Single-ended requires an air gap in the output transformer to store energy to provide bipolar current for the speaker. Now, this makes the parasitics of the transformer even worse because you need more turns to get adequate inductance to get low frequency, and more turns gives you more parasitic capacitance, more leakage inductance. Anyway, it's more difficult to get a wide bandwidth amplifier using single-ended topology. So next. Yeah.
Your previous slide showed the leakage is inductive. And I'm curious if there's a capacitive element in there also.
Now, you're referring to the slide before this, or? You're referring to the one with the leakage inductance?
With the push-pull and the single-ended amp. The push-pull and the single-ended amp. No?
Forward.
That one. Yes, sir. You showed the leakages in inductive, but is there a capacitive effect in there also?
Yeah, the capacitive is the winding capacitance in the transformer. And it's a distributed capacitance. It's not lumped.
But it's not in the tube.
I'm sorry.
It's not in the tube.
No, it has nothing to do with the tube.
Okay.
The tube has additional capacitance, but this is worse because it's distributed. So if you try and model this transformer to, to use negative feedback or any of these things that you want a more ideal circuit, this really screws you up. And this is why transformer coupled amplifiers, you can't apply much negative feedback before they go bonkers. And so it's these elements, the parasitics, that limit, how much, feedback you can do. I'll talk a little bit more of that, later. But
this one in the slide before, you shouldn't mix impedance, which is an AC parameter, with DC resistance, which is an AC parameter.
oh yeah, this is AC.
No, because when you're talking about the power, because you say like I squared R, well, R is a DC, we have to use the DC resistance of the voice coil, not the AC parameter of 8 ohms.
Right.
So the coil could be like 6 ohms or 5 ohms, DCR, but and when people say 8 ohms, it's only nominal.
It's nominal.
That could be at like 1,000 hertz.
It's an approximation. The whole thing is an approximation because I say at the end that you may only get a third of the power anyway. So, but yeah, this is part of the game when I was talking about the two equations, was balancing those equations so that you maximize your power transfer. And there are a lot of factors involved. And, one I just sort of glossed over is, no, you don't have zero output impedance on your 6v6, and you don't have infinite this and infinite that. I mean, it's all, a certain amount of, and that's going to affect that. I said that the winding ratio was 30 to optimize this. Well, it's really not when you throw in those other parameters. Everything kind of changes, but I had to kind of try and do the best I could with that. Ultralinear configuration adds some local feedback, which lowers the output impedance and distortion. The primary of the output transformer has taps to feed portions of the plate signal back to the screens of the tubes. And it suppresses gain, it lowers output impedance, and it reduces distortion. So this is a technique that Hafler and whatever came up with to, make the amplifier better. And there's a little bit of penalty in power output, but it's not too bad. And it's a nice circuit. Okay, now we'll move on to the next general topic, which is the output transformerless amplifier. Julius Fetterman was the pioneer back in 1956 or so, 55. And Philips took on an interesting idea where they said, well, let's make a high impedance speaker and do it that way. And then, anyway, carry on to the next slide. This is Julius Fetterman back in the 50s. And he'd been working, designing tube testing apparatus before doing his development work on this output transformerless amplifier. This gave him an important advantage in understanding attributes of tubes that would best suit his amplifier. Next. This is his patent, December 1956, in case you can't read that. Well, filed in 90, it looks like 53. His point, and this is important, that the output transformer, by eliminating the output transformer, you can come up with an amplifier that can use much larger amounts of negative feedback to reduce distortion. And as I was saying previously, those parasitics in the output transformer really tangle you up if you try and do anything with too much feedback. Next slide. This is his original Futterman circuit. There's some issues with it. I mean, lack of safety isolation from the power line. The power line does have a transformer for, B plus for the input circuit, but it doesn't for the output tube. So the speaker is not isolated from the power line. Yeah, that's kind of a bad thing. But anyway, let's forget about that. The one thing that's really significant about this circuit, and any modern op-amp designer would approve of this, to make a stable circuit that can have a large amount of feedback, you have to have a dominant pole. And that means a dominant place where the high frequency responses roll off. And then you really want to have minimal phase shift and roll off in other parts of the circuit. So this circuit, I just sort of analyzed it, and it appears to have at least 40 dB of negative feedback. I mean, that's very, very high for an audio power amp, and you never get there with a transformer. So the dominant pole here comes from, you've got a high impedance with the first tube, 6AU6, and a lot of gain. And then you've got the second tube that is driving, which that's a low mu triode with quite a bit of Miller capacitance. So your dominant pole is the plate resistance here and Miller capacitance here. He doesn't have to put any extra diddly capacitors in there because this works perfectly. All the other impedances in this circuit are low, so there's not going to be much phase shift. So this is really ideal design. I mean, this is really good. So even though he's screwed up on the power, this is really good. So next. So these were kind of a timeline of amplifiers that Futterman, made. And he died, I think, in I believe the late 70s. And a fellow named Harvey Rosenberg, I mentioned, right, I guess at the beginning, licensed this technology within a year before he died. I mean, it was like that, it happened that fast. And New York Audio Lab, it was the one licensing it, and then they started making it. And yeah, I guess in about 1981, they licensed the design from Futterman. So they were able to actually continue making that amplifier without too many changes. New York Audio Lab was short-lived. Black Monday stock market crash of 87. Well, that ended a lot of high-end audio companies. Next slide. So this is New York Audio Lab's offering using the Futterman in transition from triodes to TV sweep tubes. And so this is this, I believe, 6LF6 tubes, which is a very, very nice tube. I've used it myself. It's a very high performance TV sweep tube. So they made a number of different ones, but this is kind of typical what they look like. Next. Now, Philips. This was interesting because, the previous OTL design with the Futterman, it depended on putting a lot of tubes in parallel to try and get enough current, to drive the speaker. Well, I meant you had to choose your speaker pretty carefully to, for as high as impedance as you could get to, get enough current to drive it, and then put as many tubes in there to get enough current to drive, whatever. So it was kind of a stumbling block. Philips came up with the idea, well, let's make a 800 ohm speaker. So they made this radio, made a couple radios, and a friend of mine told me, well, they made a TV set with this too, but they had the speaker split between the high side drive and low side drive tubes. And so that was their solution to making an OTL amplifier without having a ridiculous number of tubes in parallel. Next slide. And this is just a more deluxe version. This is kind of interesting because they have a blocking capacitor to keep the DC out of the speaker, but then they also have an output transformer to drive a regular speaker. So this is kind of this was a more deluxe radio, so maybe they had I don't know, maybe a bass speaker and that they would needed a transformer. I don't know. But this is just sort of interesting that they had this. But again, it's the push pull with the totem pole or this kind of arrangement. Next slide. And this was a cheapish Philips radio, which I guess other companies put their name on that maybe they were all made by Philips. I don't know. But this one was kind of interesting in that they just said, well, we're not even going to worry about push pull or, we don't care. We're just going to have DC current in the speaker. So that's what they did. Just, I don't know whether they made the speaker special so that the magnetic flux or whatever from the DC didn't just peg the cone to one side and then, maybe they made the speaker that you actually had to put it in the right polarity to make it so that it didn't pull the cone in, too much. But that was kind of an interesting, inexpensive approach to this. Note that it's a 700 ohm speaker. Next, they even made a hi-fi amplifier for high impedance speakers. So this 1955. This amplifier was produced. Next slide. So then came a grand proliferation of OTL amplifiers out of the 80s, 1980s. Just many companies were involved in putting a whole lot of tubes in parallel and, and making amplifiers. This is a kit. This is a DIY project. This company is Atmosphere. They're still very active making these amplifiers. It's one of the more respected ones. And then there were a lot of other ones that kind of came and went. Some may still be made, but mostly they came and went. Next slide. Okay, now the next big section is the ZOTL. And this gets pretty technical in places too, so bear with me. The DC-DC converter is really impedance conversion. When you buy a Chinese power supply or whatever to convert 120 volts to rectified, maybe and rectified and doubled maybe 350 volts into 12 volts or what have you. I mean, it's DC to DC conversion technology, and you're changing impedance. The line the high voltage side is high impedance because it's not drawing much current. On the output side is low voltage, so it's much lower impedance because you're putting out a lot of current. So basically, DC to DC converter is really impedance conversion. I'm just going to talk about the topology and the patent I got with it. Single end versus push pull. Now this gets pretty technical too. The impedance conversion ratios, and I'm going to compare the output transformer versus the ZOTL, and very important is reflected impedance. Frequency response limitations, special configuration, how I do the ultralinear with the ZOTL, and the performance compared to output transformers. Next. Okay, so as I said, DC to DC power conversion, and it's fundamental to the ZOTL. So look, I'll try and go through this quick lesson. switch 1 through switch 4, these are MOSFET switches in what's called a full bridge. They alternately commutate the applied DC supply voltage, V plus, to the primary of the transformer, first in one polarity and then in the opposite polarity. This applies AC to the transformer that can be stepped up and down, or stepped up or down in voltage. So switch 1 and switch 4 are closed at the same time. So that applies the V plus to this side of the transformer. And then on the next switching half cycle, switch 1 and switch 4 are opened, and switch 3 and switch 2 are closed. And that applies the return, or 0 volts, to this side now, and it applies V plus to that side. So you get a square wave through your transformer, and I've represented that here with a voltage that is the number of turns N2 divided by N1 times the V plus voltage. So that's what the amplitude of this is, but it's, it's a square wave. And so for that half cycle, you get this, and then when you switch over to this, where switch 1 is open, switch 4 is open, then you get this phase. So you got phase 1 and phase 2. Those are combined with the rectifier, and you get ideally just a constant DC voltage. So that's the secondary AC voltage is converted back into DC voltage for the load by a four-way bridge rectifier. In the ZOTL, that load is a vacuum tube modulated in conductance by a varying audio signal. That's important. In the ZOTL, that load is a vacuum tube modulated and conducted by a varying audio signal. So that's a lot to swallow, but take my word for it for now. Let's go to the next slide. This is the patent for the ZOTL, and I'm going to try and read some of this because I'm sure you can't see it. Linear audio amplifier includes a push-pull pair of vacuum tubes that are operating in a linear amplifying mode coupled through a pair of DC to DC switching power converters to an external load impedance, that being the speaker. Each power converter includes a transformer with one or more secondaries, windings that drive rectifier circuits, and the resultant DC voltage sources are loaded by their respective tubes. I won't say any more of that, but this is the fundamental circuit for half of it. This is like the positive half, and this is the negative half. The inverted signal through its tube drives this half, and the non-inverted signal through that tube, it drives that half. And then the two are combined to drive the loads, which is a speaker. Next slide. So this is better detail really of how the tube controls the speaker in the ZOTL. And this is, pretty fundamental. It's probably the most important slide in the whole talk. So I want to emphasize there's no power gain in the ZOTL. Like an output transformer, there's no power gain, just impedance conversion. But that's important. Now let's see, I guess this is the best order to do it. Note that the V plus, or the plus V voltage, whatever, is applied to the series combination of the commutating bridge transistor, these things, which are MOSFETs, and the speaker, and that only a portion of the V plus across the bridge is being modulated. It's amplitude modulated and applied to the primary of the transformer. the primary being on this side. And the remainder is unmodulated and applied directly to the speaker. So this is kind of like a voltage divider. You got the speaker taking, a portion of the voltage, and you got the, this MOSFET bridge taking a portion of the voltage. And that portion of the voltage is what is modulated and carried through the transformer, rectified and applied as a DC voltage or a varying DC voltage to the plate of the tube. The plate to cathode voltage on the tube follows this equation. It's the voltage, it's V plus minus the speaker voltage times the transformer ratio, N2 over N1, now demodulated by the rectifier bridge. So it's a mouthful, but that's, basically how the ZOTL controls the speaker. There's some features. Input is isolated from the output, just like an output transformer. The reference return for my input signal is not connected to the speaker, or it doesn't have to be. So what this does is you can have a multi-stage amplifier, which you can do DC coupling, because this part is independent. You can have the cathode of the driver tube, or the output tube rather, sitting up at plus 300 volts. And I do that all the time in my amplifier designs because I want DC coupling, and I have cascaded stages, and by the time you get to the grid of the output tube, you want to be up at 300 volts or what have you. So this allows you to do that, and yet you get DC coupling through this scheme of modulation. So this is a DC coupled amplifier, but you have this isolation for DC where you want it. So that's a nice feature. So the conductance of the tube is modulated by the audio signal, and the conductance of the MOSFET commutating bridge changes accordingly by loading through the transformer. This modulates the audio frequency voltage applied to the speaker. So as you're modulating the impedance of the tube, it's in turn modulating the impedance of this MOSFET bridge. And so when the tube turns on harder and drops, it gets a lower voltage plate to cathode, it turns on it lowers the impedance of the MOSFET bridge. So by lowering the impedance of the MOSFET bridge, there's proportionally less voltage across the MOSFET bridge and more of the voltages across the speaker. So turning the tube on harder results in the higher voltage applied to the speaker. And that's a DC voltage. What I mean is it's a low frequency, it's an audio signal voltage. It's not the RF modulated frequency, which by the way is about 250 kilohertz normally, although I've done higher. But so that's, this is, as I say, the meat of it, the most important part of it. Next slide. So this can be done single-ended amplifiers, push-pull amplifiers. So these are, just alternative ways you can do the ZOTL. So typically 250 kilohertz transformers. They just do one frequency. It's amplitude modulated through the transformer, but just one frequency. So the as I said before, there's no energy, no low frequency limit. So it can do the DC. Now, in the single-ended application, you have to store energy because with a single-ended circuit of any topology, you have an active device which can push the speaker in one direction. You've got to have a means to pull the speaker in the other direction. You can't just put, pulsating DC into the speaker. So with an output transformer, that energy storage comes in form of the air gap. An output transformer requires an air gap to store that energy. If you don't have the air gap, it saturates and it can't store energy. So that's why you have to have the air gap. So I don't have an air gap. I don't have an output transformer. So what do? Well, one thing I can do is I can put a choke across the speaker like that, and that will provide a current, a DC idling current through this whole circuit. So the tube has an idling current, the MOSFET bridge has an idling current, and there's an idling current being fed into this choke speaker combination. Now, under no signal conditions, meaning just an idling current but no AC audio signal, the speaker has ideally no current because the choke is, it's ideally the DC impedance or DC resistance of the choke is 0. So all the idling current is passing through the choke. Now the idling current is the idling current in the tube, times this transformation ratio, which, you've got low current, high voltage in the tube while you got high current, low voltage there. But so chokes aren't ideal. I mean, this is kind of a technicality. They're not ideal, so you can't just really quite ground the choke. You got to apply a little bit of negative voltage, depending on the DC resistance of the choke itself. You need to offset and account for that DC resistance in the choke. So you apply a little bit of negative voltage, to that end of the choke rather than having it grounded. But that's just a little technicality. Basically, it doesn't change the operation of the circuit. Next slide. So yeah, let's review the output transformer matches the high tube voltage impedance to the low speaker voltage impedance. Power is fed into the system from the primary side with tubes at high voltage. So this is the output transformer, not the ZOTL. Bandwidth is limited at high frequency by leakage inductance and parasitic capacitance. Low frequency limited by magnetizing current and saturation. Parasitics reduce the amount of feedback that can be applied to lower the distortion and output impedance. It's a simple AC coupling concept. As I said, this is a review because I already said all this. So next slide. The ZOTL. So I want to compare that. The ZOTL transformer parasitics are not shown, but they're similar to an output transformer. Parasitics affect efficiency in both positive and detrimental ways, but do not affect the frequency response. I don't want to get into the technicalities of how the parasitics can improve efficiency, but they can. But yeah, it's anyway, the difference is power is fed into the system from the speaker side, which is now the primary at low voltage. The high frequency bandwidth is limited by optional noise filters, which I didn't show any. There's no low frequency limits, and DC, it's a DC to DC power conversion concept. Next slide. Now this gets kind of, difficult to follow maybe, but the first thing I think should probably say that turns ratio, converts, one voltage to another by the actual number of turns ratios, or the turns ratio of the transformer can changes the voltage by a factor of whatever that turns ratio is, and changes the current in the opposite direction but that same turns ratio. Impedance goes as the square of that turns ratio. So that's just a characteristic of transformers and whatever. So let's look at reflected impedance with the transformer first. So I put this big arrow to the transformer. And by reflected impedance, well, maybe it'll be clear. So the overall turns ratio is 10-to-1 plus 10-to-1 because we got these this arrangement here. So overall, we have a 20-to-1 plate-to-plate impedance, which goes as the square of the turns ratio. So the impedance conversion is 400 for this circuit. The 8-ohm speaker presents 3,200 ohms to series connected tubes plate to plate. So if we look back in this direction, the speaker, we multiply, we got 8 ohms and we got the 400 ohms. So we multiply those together and we get 3,200 ohms as, the tubes together in this push-pull arrangement see 3,200 ohms as their load that they're driving. But under large class B signal or operation where one tube is turned off and the other is on, then the speaker presents 800 ohms to one tube at a time. Because you're only dealing with half of the transformer on this side. So it's just the secondary to this half of the primary. So the impedance, that one tube that's active is seeing 800 ohms. Now, another way to look at things, suppose each tube has a plate resistance of 2 kilo ohms. Each tube reflects 20 ohms to the speaker through half of the transformer. So 2 k ohms on one tube, and we got this turns ratio, and we get the impedance of the speaker seeing 20 ohms from that one tube. Now, under small signal conditions, now small signal conditions are, you do things when you analyze small signal is a power supply is treated as a ground. And this is just the way small signal analysis is done. So what that implies is under small signal conditions, the tubes can be treated as being in parallel, not series. And the reflected impedance of the speaker now is really 10 ohms under small signal conditions. That's when both tubes are active. As I said, the B plus is ground, the cathode is ground. So these are like two resistors, but they're in parallel because of the ground here. So the speaker, the reflected speaker to the speaker is 10 ohms from the tubes. So try and remember those numbers. Next slide, please. The ZOTL, we're going to go through the same argument. But it's maybe a little harder to follow. I don't know. Suppose again, each tube has a plate resistance of 2K. Each tube reflects 20 ohms to its respective full bridge commutating set. Okay, so that's large signal conditions. One tube is on, the other tube is off, the other tube, the commutation bridge is high impedance, so it's not in circuit. So you're looking at, half the circuit. And so a tube reflects 20 ohms. Again, we're doing the same ratio, 10 to 1, that we did with the output transformer, 10 to 1, with that high frequency transformer. So each tube reflects 20 ohms to its respective full bridge MOSFET commutation. But the total reflected impedance of the speaker is 10 ohms under small signal conditions, again, because, these are, in this case, the commutating bridges are in parallel, not, this is, whereas these were in parallel, but the commutating bridges are in parallel. But anyway, again, the reflected total impedance to the speaker is 10 ohms. Gee, that sounds like the output transformer. The two MOSFET bridges, as well as the tubes are in parallel to the ground under small signal conditions. Under large signal conditions for class B, one tube is turned off. Its respective MOSFET bridge presents an open circuit. Then the 8 ohm speaker presents 800 ohm load to one active tube through the active MOSFET bridge. Boy, that sounds familiar too. Under small signal conditions, the 8 ohm speaker presents 3200 ohm plate to plate with overall impedance conversion of 400. Again, those are familiar numbers. Note that the plate to plate configuration terminology is used. The two tubes are in series as far as loading. Thus, each 2K tube has to make 4K with overall conversion 400, resulting in parallel source impedance to the speaker like we had before. As I said, you really have to think about this. I don't expect anybody to really follow it very well, but I wanted to present the technical issues just so I'm not just lying about stuff. So anyway, next slide. So just to summarize, in the ZOTL under small signal conditions, the primaries of the converter transforms in parallel, the secondaries are in series. The commutating bridges become part of the primaries and the bridge rectifiers become part of the secondaries. Thus, the ZOTL becomes identical to the output transformer for the treatment of reflected and transmitted impedance. Only the names primary and secondary switch places as power is fed into the system on the primary side in both cases. So I just, this is the primary for the output transformer, and over on that one, the speaker is on the primary side. The commutation bridges do not act like buffers. The tubes see and react to any impedance variations with frequency that the speaker presents. Same occurs with an output transformer. What this means is your speaker isn't 8 ohms. It's some weird combination of inductance, capacitance, and back EMF and all kinds of weird stuff. And the point I want to make with this reflected impedance and why it's so important is the ZOTL works just like an output transformer for back EMF, damping, how it responds to weird reactive loads and all that stuff. I mean, it works exactly the same way as an output transformer. So next slide. Now here are some additional differences not related to normal audio reproduction. This is sort of interesting, but probably not of too much consequence. The ZOTL will not impedance match a signal with the same frequency as the carrier frequency. In other words, if the carrier frequency is 250 kilohertz, it's not going to match that. If you put 250 kilohertz into the tube, it's just going to, short itself out. It's not going to do anything. There are minor signal amplitude variations that are present if those signals are harmonically related to the ZOTL switching frequency. Those are pretty minor, but they are present. The ZOTL, now this is interesting, the ZOTL will impedance match signals higher than the switching frequency, unlike a digital system or most carrier systems. So you could put, 300 kilohertz into your tube and it'll do it. It'll match it. Next slide. The ultralinear implementation on the ZOTL can be done. Now, when you do the ultralinear, which I neglected to point out, with an output transformer, the plate voltage and the screen voltage, the DC value of those voltages are about the same because it's just an output transformer doesn't have a significant amount of DC resistance. So for all intents and purposes, the DC component of the screen voltage and the DC component of the plate voltage with an output transformer are about the same. With the ZOTL, that's not the case with this type of arrangement, because what I do with the ZOTL is I break in fact, I do this all the time anyway to get better performance. I break the the secondary down into numerous individual windings, each one having their own diode bridge, and all those bridges are stacked in parallel. So typically in a ZOTL amplifier, I might have 8 or 10 or even 16 of those bridges stacked in parallel. Technically what that does is it improves speed. If I put all the turns on one winding, there's leakage inductance, which ruins the fidelity of the 250 kilohertz square wave. So the way to get around that largely is to break that down into small low number of turns windings and put a whole bunch of these bridge rectifiers in series. So I do that normally. So I can use that scheme for doing the ultralinear. So what I do is I put like say 8 of these bridges in series for the plate, and then I tap off maybe 4 bridges down and put half the voltage into the screen. So in the case of the ZOTL ultralinear, the DC component of the screen is, if I do it that way with 4 and 8, the DC component of the screen will be half of what the plate DC component is. That's pretty useful for a lot of tubes that can't handle the screen voltage. Or alternatively, I can put much higher voltage on the plate than the tube is rated for, because breakdowns in tubes due to voltage are caused by high fields in the grid to cathode region, or but the plate is separated from all those. So you can put a much higher plate voltage on the tube than you might think you could, provided you keep the screen voltage much lower, because the screen voltage actually determines what the bias on the cathode to grid is for a large extent. So that lets you have a lot more. You can get more power output, by using a lot more voltage on the plate than what you normally be able to use. So this setup for the ultralinear is quite useful, because it does the same thing that happens with an output transformer. It lowers the output impedance. It gives you some local feedback, reduces distortion, and so on and so forth. So it's just like the ultralinear with output transformer. Gives you the same advantages, but widens your available tube selection. So next slide. So let's look at some performance. The output transformer, 10 kilohertz square wave. This is a good output transformer, by the way. It's not a piece of junk. And but that's the square wave. With the ZOTL, 10 kilohertz. I mean, it's just much faster. Next slide. This is a curve tracing of, in this first case, ZOTL, a triode connected 6L6. So these lines represent, in case you're not familiar with the curve tracer, and probably a lot of you aren't, these are steps in your applied grid voltage, and these are the plate voltages on this on the x-axis. The plate current is the y-axis. The parameters per vertical division, 20 milliamps, step up. The plate voltage, 100 volts per step, up. The grid steps are 10 volts. This one is 0 volts, minus 10, minus 20, minus 30, or minus 30, 40, 50, and so on, up to minus 100 volts. This is a transconductance. So this is a triode connected 6L6 curve traced through the ZOTL impedance converter. It looks pretty much the same, but look at the parameters. This one has the vertical per step 20 milliamps per per step here, per line here. This is 1 amp per line. So you got 1 amp, 2 amp, 3 amp, 4 amp, 5 amp, 6 amp, and so on. The plate voltage, 100 volts per step, 100, 200, or this is 0, 100, 200, 300, 400, and so on. That one's just 2 volts per step. This is 2 volts, 2 volts, 4 volts, 6 volts, 8 volts, and so on. So that's completely impedance converted from this one to that one, in that you're changing from this high voltage, low current to the high current, low voltage. Note the change in the transconductance. Huge. 2 here. I think this is millisiemens now. I think that's a term they use. 100 millisiemens. I mean, that's a huge change. So this device, if you look at this as a device, boy, isn't that great for driving the speaker? Look at all the current I get, and I don't need that much voltage. So, that's super. The steps are the same, 10 volts per step. So anyway, next. So this is kind of where the zero hysteresis comes in. This is a push-pull 6L6 is triad connected and curve traced through an output transformer. I've always been known for using curve tracers in weird ways, and this is a case in point. Curve tracer that I have is made for testing transistors, but yeah, what's to say you can't curve trace a transformer or a device for a transformer? So that's what I did here. A pair of 6L6s, put the curve tracer in the AC mode. So you've got, this quadrant, you've got the triad curves, and then these are inverted because this is the opposite phase of the transformer. So I did the same thing over here. Push-pull pair of 6L6s triad connected and curve traced through the ZOTL impedance converter. So now these parameters are the same on both, because I've chosen this output transformer that I used here to have the same, more or less the same impedance conversion ratio that I did on the ZOTL. So that was just a choice I made to, make these things look pretty close. So all these hysteresis loops and goofy things and this and that, with the ZOTL, they're all gone. So these are the things that are actually most responsible for the sound of a tube amp. This is kind of the woolly bass, the detrimental qualities of a tube amp, I should say. The woolly bass and kind of, some inaccuracy in the reproduction of some of the musical instruments. This goo, I call it, is, responsible for that. The tubes are not. The tubes are, they're faithful to the reproduction. So next slide. This is one of the higher powered amps I've made with the ZOTL. So audio circuit is pretty simple. Essentially no coupling caps. It's just all DC coupled, pretty much. I have one input blocking cap, but that's it, to keep, DC from a preamp from making DC onto the speaker. So the power supply, which is power factor corrected, it's got a parallel resonant converter for getting all the voltage. The ZOTL impedance converter on this one are this section here, which is quadrature. Because of the high power and that I was charging a lot for this amplifier, there's some non-ideal characteristics of the ZOTL impedance transformation that prevent you from having perfect square waves. So I get around that imperfection to a large extent by using what I call quadrature, which is really interlaced power converters. They use this in microprocessor power supplies all the time. They use this, what they call interlacing in the power supply. to get enough current for a microprocessor at low voltage. So this amplifier is one that's very robust against driving weird low impedance loads because of all this. Lots of energy storage capacitors. That makes for great, for better sound. So that's that's one of my more expensive amplifiers. Next slide. Even more crazy is the people that buy some of these amplifiers. I have a partner on the West Coast that sells these things. I can never sell anything this ridiculously expensive, but his clients, this horn speaker is $1 million. So his clients have no problem at all spending $200,000 for a ZOTL amplifier to drive them. Part of the reason it's so expensive is it's got a 30-pound silver wound choke for each one. These are mono units, single-ended 845s. And there's a story about this. A lot of these people that put these systems together like this, they're in their 80s and they really can't hear anymore, but they want to impress their friends. So this fellow was happy to invite this audio magazine reviewer in to take pictures of the system and put it on the web and whatever. So that's why I'm showing it here. Is next slide. So just the ZOTL technology is now licensed and made affordable by a local company here in Tacoma Park, Linear Tube Audio. So unlike a lot of the other stuff in this series of talks here, this is actively available for sale, whereas 1980s computers are no longer actively available for sale, or a lot of the stuff here with the antique radios is no longer made, of course. So anyway, that's my talk, and I'll take some questions.
So David, how do you generate the 250 kilohertz switching frequency?
Where do I generate it?
Well, how? How do you generate it?
Oh, how do I do it? Just an oscillator. Yeah,
Oh, we got an oscillator.
actually, what I do is my power supplies are 250 kilohertz. So I just take some of that. If I use a different frequency in the power supply from the ZOTL frequency, there are opportunities for intermodulation
Yeah, I was going to say.
issues.
Yeah.
So I like to, use the same frequency. I haven't done that in all my amplifiers. That big 200-watt monster I showed, the power supply is actually 70 kilohertz. And then there's a separate oscillator to get to 250 kilohertz. That's not so bad for that one because the output tubes are indirectly heated. But a lot of my amplifiers use directly heated filaments like 845 or 6B4G or whatever. And if you use a different frequency on the filament that you use from the ZOTL, you're going to get all kinds of weird lining and other stuff.
Yeah.
So that's why I, combine the power supply frequency with the ZOTL. Now there is another frequency, and I do have to be careful of this one.
Okay.
The power factor correction. Now the power factor correction I put in there for a couple of reasons. One is it's a universal line voltage. Somebody anywhere in the world can just plug it in and not have to worry about changing the voltage.
Okay.
The other thing it does is and the real reason for power factor correction is it makes the current draw off the power line sinusoidal and in phase with the voltage. And so normally, if you don't have that, in charging with each cycle in charging capacitors, you get a big current spike and then the current zero.
Right.
So that's very undesirable. In fact, it's illegal with, a lot of the new requirements. If your power supply is over a certain power level, it has to be power factor corrected by FCC or whoever's involved, FCC or I'm not sure. But most anything you buy now that has a substantial amount of power is power factor corrected, at least in name. Now, I've seen some weird stuff done. Leave it to the Chinese to find a way to get around the rules. And I'll tell you a story of one of those. Is I bought a cheap Chinese power supply which advertised power factor correction. Well, no, it's not. What they did is they modulated the switching frequency on the power supply so that it would spread a band out on a spectrum analyzer. And so it met a requirement that there was no big spike at any particular frequency. It broadened this into a bunch of noise, but it still had the current drawing big spikes. So,
well, that's what I was going to ask you next is how did you decouple? Because I was looking at the overshoot on the square waves that you showed, and I was wondering if that's coming from your switching frequency.
No, that's generally speaking, that's just parasitics. Usually now what I showed you with the square wave at 10 kilohertz,
right?
That's really a lot better than when you buy one of my amplifiers that you really get. And the reason is I have output noise filters.
Okay, that's what I'm going to ask.
And so those make ringing as well because I have a inductor and then I have a capacitor.
Right.
And so if the output impedance is too low, I use some damping resistors to kind of control that, but it's still there to some extent. But with that particular demonstration, I said, I'm not going to put the filter on. I'm going to make this look, really good. So, but it's still good. It's just not quite as.
Okay, one more question.
I'll leave a copy of the talk up here, and anybody can look at anything that they want.
Could you substitute a transistor for the 6L6s? Could you make the whole thing solid state?
You could. You could. There's not much point in it, but you could, because you don't. With the solid state devices, why impedance match? I mean, they work with speakers just fine the way they are. But the way I wrote the patent is it would allow that. Because I didn't really specify tubes as being in the claims. When I got to the claims, it included transistors if you wanted to use them.
Okay.
Okay, thank you, David. Kind of went over my head, a lot of it, but I'm saturated with it. So thanks, David.